Okay, the next clustering algorithm which we will be doing is Dbscan. The term Dbscan is the full form of density based spatial clustering of applications with noise, right? Basically the last algorithm which we did was density based clustering. This algorithm is also density based clustering, and all of these density based clustering basically utilize graphs um, to group the data, right? No, this one is not included. Now the most of the partitioning or clustering algorithm method cluster objects based upon distance between them, right? Um, Now such methods can find only spatial or spherical shaped clusters, and they find it challenging to find a cluster with arbitrary shape, right? As if you recall, I told you about the k-means clustering. Um, for example, this is the center of the cluster, so we will be trying to find all the clusters or items which are with or near to this blue point. So the shape the shape of the cluster will be sort of a sphere, right? But in case if we have a non-spherical circle, for example, if you see here, this is a non-spherical cluster, right? Now extracting this cluster based upon the distance based method is quite challenging. So therefore the density based clustering methods are appropriate to extract such irregular shaped clusters. So the previous algorithm which we did, the density based clustering and this Dbscan, both of them are appropriate for such formation of clusters, right? So if you see here, there are three groups, orange, blue and green. And if you see here, the green points, the group of green points, which is basically cluster, is non-spherical by its nature, whereas the group of these blue points is sort of spherical. But if we opted for k-mean or k-medioid clustering, this green cluster could not have been identified, right? Maybe those clustering identify this in maybe 2 or 3 groups. So the general idea is to continue growing the given cluster as long as the density in the neighborhood exceeds some particular threshold, right? Now, for each data point within a given cluster, the neighborhood of a given radius has to contain at least a minimum number of points, right? So this is an important concept in Dbscan. Now such methods can be used to filter out, this Dbscan is very efficient to filter out noise, because if you see here, these gray points, they are not part of any cluster because they have very low density. So these all points are regarded as noise. So the Dbscan or the previous one, the density based clustering, are very useful to identify the outliers and noise. At times these outliers are very important patterns as well. So at times you need to inspect them manually as well. Now coming to the concepts which are used in the Dbscan, which I mentioned here as well, that the number of data points for a given radius is important, but let us now formally go to the technical details. Now the neighborhood within a radius E epsilon, I may use the word E here or epsilon interchangeably. The neighborhood within a radius epsilon of a given object is called the E neighborhood of the object, right. So, this is the first term which is used in this Dbscan algorithm, which is the E neighborhood of the object. The next term is the minimum points, right. So, in this particular algorithm we will be given before starting or executing the algorithm, we will be given a minimum number of points, or we have to give minimum number of points as a starting parameter to this particular algorithm. Now, what is the influence of this parameter? For example, we are given minimum number of points equals to 3. So, what we will be doing? We will be selecting an object, if you see here. Now, within its E neighborhood, the distance of E can be any distance measure. We have to see that at least this much points should be there, right. So, if you see here this red point, within its E neighborhood 3 points or 3 other nodes of the graph are available. So, this makes this red point a core object, right. Now, if you see here in this example, within the E neighborhood there is only one point which is less than the minimum points required. So, this particular point is not the core point, right. So, there are three concepts: E neighborhood, min points, and the core point, the core object, right. Then once we have identified the concept of neighborhood and a minimum number of points and the core object, the next task is to identify the reachability concept in a Dbscan. Now, we say that an object P, here we are calling these nodes object, you can call them nodes or vertices. We say that an object P is directly density reachable from a core point Q if this point P is within E neighborhood of the Q, right. So, this is a core point because within its E neighborhood there are at least minimum min points like 3 points. So, this point P is within this E neighborhood. So, it is directly density reachable, right. Okay. Now, the next concept is density reachable. Point to be noted is that the previous one was directly density reachable, but this the next concept is density reachable, it is not direct, right. So, an object P is density reachable from an object Q. This object P we have to reach there, and we are here at Q, and we are density reachable if there is a chain of objects where P1 is equal to Q and so on and so forth, and these are directly reachable. For example, you cannot directly reach here, right? You cannot directly reach here because the distance here is greater than epsilon, right. But what you do, you reach here another core point, and from this core point you reach this point, right. So, in this way you are density reachable, right, instead of directly density reachable, right. So, we got two concepts: density reachable, directly density reachable, and density reachable. Now, an object P, this is sort of redundant. Okay, let me read it again, maybe something new. An object P is density connected. Okay, yes, I misread it because this concept is density reachable, but this one is density connected, right. So, but this is the same concept as that of the reachability concept. And object P is density connected to object Q. Object Q if there is an object O such that both object P and Q are density reachable to O, right. So you are here and the point where you want to reach is this one, but they are not within epsilon neighborhood. However, you end up finding a point O which is like reachable from P and Q as well. So if via this object O you are density connected with object Q, right. So right, so this here is an example. Okay, let me change the color. Here in the example where you see that these point M, P and O are core objects provided then that min points are 3. Okay, let's see M, where is M? This one is M. If you see here, we within this E neighborhood we have 3 points, 1, 2 and 3. Okay, this is core, fine. Let's see P within the E neighborhood of P we have 3 points again, one is M itself. So within the core points E neighborhood we can have another core point as well. So never mind that. So here this P is also core point, and if we see O, I cannot see O. Okay, I think this one is O, yes. So if we see O, within this O we have got this 1, 2 and 3 points, right. This is minimum 3, by chance every point object had 3 points within the neighborhood, but they can have 4 or 5, but minimum 3 is required to be eligible to become a core point or core object. Right. Now P and Q are directly density reachable from M. Okay, this P and Q are directly reachable from M, like this M can directly go to Q and this M can directly go to P, right. This is fine. And Q is density reachable from P, but P is not density reachable from Q, right. So that is very obvious. So this was an example of various concepts which we learned so far. Now the actual question still remains is that how will we ultimately extract clusters using these concepts, right. So for this these definitions, or rather these are sort of redundant concepts, I think. The definition of clustering here is this one using Dbscan concepts. So a cluster is a set of density connected objects with the maxima which is maximal with respect to density reachability, like. So we need to find density density connected objects, for example this one and this. Okay, let me change the color, okay, maybe green, for example this one and this one and this one, so that the reachability distance is the maximum. So this will become a cluster using Dbscan. Now in the form of algorithm, the Dbscan works like this: arbitrarily or randomly select point P, retrieve all points density reachability from P with respect to E and min points. For example, E is, let's say, some variable distance measure 7 and min points is equal to 4. So you will have to find the reachability, retrieve all points density reachability with respect to P, right. If P is a core point, a cluster is formed. If P is a border point, no points are density reachable to P, then what Dbscan will do, it will visit the next point of the database, and this process will continue until all points have been processed, right. So for every point we will at least perform these 2 steps, and if the point turns out to be a core point, that will become the cluster, right. And among these so many clusters, we have to find the set of connected points which are longest or the maximal in terms of density reachability, So this particular algorithm has many advantages. For example, one of the obvious advantage of this algorithm is that it is not dependent upon the any number of clusters we need to know beforehand. For example, for in k means or k medioids, we needed to provide the value of k which is always greater than or equal to 2, 2, 3 or 4. Here we need not know to know the initial guess about the number of clusters in the data. So this is an advantage, but of course we will have to give parameters to the algorithm like the epsilon, the radius and the minimum number of points. These two will be provided to the algorithm. And the Dbscan does not have a bias towards a particular cluster shape, because it can it's not like that it always extract a spherical shaped cluster. It can extract different irregular shaped clusters as well. And Dbscan is, of course, this is one of the major advantages of Dbscan, that it is resistant to noise. And if the noise is there in the data set, it can easily ignore that and it can easily identify that as outliers. These are the benchmark results of the original contribution of the Dbscan, the paper which was published, and these are the original results of that. And if you see here, the Dbscan has identified spherical shaped clusters as well, but if you see here, it has identified different shaped clusters as too. For example, this Y has been extracted, and the data sets which are used for clustering are of various types. For example, in the recent assignment which I have emailed to you, I have given you the iris data set. So to test the capability of a clustering algorithm, you can test it on the benchmark data set, and if that clustering algorithm extracts the required number or required shape of cluster from the data, it means that the clustering algorithm is producing the desirable results, right? So this is the reference. You can see it, and for example, this is a bit of the old clustering algorithm, but it is very important one as well, because based upon this Dbscan, you can develop new algorithms. And this Dbscan is a bit older, but the density based clustering, which is a lecture which was, I think, week 11 lecture, is the newer version of the Dbscan. But if we see, I would like to see the number of citations of this algorithm. Okay, let me open this article, and if you see here, this has 19,514 citations, right? Again, it was published in 1996, but there are many other algorithms which were published in 1980, and they have less than 10 or 20 citations. So it means that this algorithm has been widely used, and this is the original article, although it is black and white here, and I've somehow obtained the colored version of the figures, right? So that's all about Dbscan, and in the next lecture we will be doing optics, which is basically the extension of Dbscan for a different sort of applications.